Okay, so I think I figured out how I want to talk about this. So the way that I've done it is a little bit backwards, but that's okay. We'll figure it out. It'll be fine. So what I've drawn in is we kind of have this area vector. So we said that that is perpendicular, perpendicular to the area of our loop. So we're kind of saying, hey, this is our loop. The area vector is just normal, perpendicular to the actual area itself. So what we have is we can kind of draw out for each situation how the area vector is related to the magnetic field vector. And then we know that we have this equation that says our flux is equal to b times a times cosine theta. And if we're thinking about this physically, our flux is just the amount of magnetic field that is going into our circle, or into our loop of wire. So this beginning case, we said, okay, we're starting with 0. And then mine's going to be upside down, but that's okay. Then we're saying, oh, well, we care about, for the flux, this angle between the magnetic field and the area. So the angle first was just 90 degrees, right? Over here we have this B, or the A, they're 90 degrees apart. Over here, I'm just kind of estimating. I'm saying, oh, okay, and it grew a little bit, so it's a little bit more than 90. So in this case, we're going to say, oh, okay, it's changing. And then it's going to be changing until eventually we reach 180 degrees. And because this thing's spinning at a constant rate, its change in theta over time is just going to be a constant. So it's changing at this constant rate. So then we have, this is going to increase with theta, or cosine of theta. This is going to change with cosine of theta until eventually we reach 180 degrees. So we're at some sort of point where we're maximized, where this function looks like cosine. So it's kind of curved like a cosine graph. Then on the way back, we're starting to then decrease the amount of magnetic field that's going through there. Before we had this maximum, and now we're kind of like this situation, but mirrored. So now we're going back to decreasing until we get back to 0. The actual answer has us like that, but same difference. And it's going to follow this cosine curve too, because it is a cosine graph. So we can think about it through the math, thinking, oh, this is just going to be a cosine, or we can think about it theoretically about what flux actually means. So our answer is going to be this E if it loads. There it is. So it's going to look like this cosine. And then eventually it will get to be, because the area vector, like I just did in mine, the area vector, the magnetic field are like that, versus what they would have had where it was like that. So the area vector, I forget how you find the direction of a normal vector, but I think it's just kind of defined. Alright, so for 5, a small rectangular object of unknown material is examined in the laboratory. Iron filings and a compass needle are not attracted to this object. The object is suspended from a light string and is free to swing, but does not align itself with the Earth's magnetic field. A strong magnetic field is switched on perpendicular to the long axis of the object. The object changes its orientation so that it partially aligns with the magnetic field. After the field is switched off, the object and string eventually return to their original orientation. Once again, it is observed that the iron filings and a compass needle are not attracted to the object. The object is most likely exhibiting the property of one of these. This really comes down to definition. We had something that was not magnetic. So something that was not magnetic, and then it could become magnetic in the presence of another magnetic field in a B field, and then is no longer magnetic after that. So that really leaves us, we said ferromagnetism is stuff that becomes a, that's not ferromagnets. Diamagnetism is going to do the opposite of a paramagnet, so it's going to oppose it instead of attract it, so that's not what happened here. So we know that we're going to have paramagnetism because it was temporarily magnetic, and then it aligned with the magnetic field. It did not disalign as a diamagnetic object would have done, and then this one makes no sense. Where's the rest of my stuff? Okay, so for the last two, with this one, we're saying a rectangular wire loop is at rest in a uniform magnetic field B. of magnitude 2 teslas that is directed out of the page. The loop measures 5 centimeters by 8 centimeters, and the plane of the loop is perpendicular to the field as shown above the total magnetic flux through the loop. So we said flux is just going to be our magnetic field times our area. So we have an magnetic field of 2 teslas and an area of 0.08 times 0.05, and that's 2 times 0.08 times 0.05 is equal to 0.008 Tesla meters squared. One thing that tripped me up when I did this one was we're used to saying, oh, the change in flux over time is, or the EMF is 0 if our change in flux over time is 0. Here we have a stationary loop, so it may be like tempting to choose 0, but flux is just how much flow do we have? How much flow do we have through our field, or through our loop of wire? So in that case, we have a constant magnetic field, constant area, but we still have a flow through it. So it's not 0, it's this 0.008. In the last one, we're saying the magnetic flux for each turn of a 20-turn coil decreases from 0.30 Tesla meters squared to 0 in 2 seconds. The EMF induced in the coil is most nearly. So in this case, we're saying what I'm going to do first is just analyze one loop of wire. So we're saying in one loop of wire, the flux is 0.30. The change in flux is 0.30. Our change in time is just going to be 2 seconds. 2 seconds. So we can figure out the rate of change of this flux for one loop, and we get 0.30 divided by 2. So we have 0.15 volts in one of our loop, but this is happening 20 times. There's 20 turn coil, so we really have 20 times 0.15 volts. This is happening to us 20 times 0.15 per each loop. So we end up with 3 volts. All right, so that is all of them for this day's work.